Okay. All right. So, talking about molar conversions today, the first thing that we want to talk about is this quantity called a mole, right? So, a mole is basically a unit. Is that the best way to say that? It's a number that allows us to go between the atomic and molecular scale which, as hopefully you guys remember, is really, really, really small, to things we can measure in the lab. Right? So things that we can measure, things that are tangible, things that we can hold, right? So when we're talking about atoms and molecules, we're talking about a scale, a nanoscopic scale. These are really, 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 really small things, right? In order for us to be able to talk about the number of atoms or molecules in something that we're measuring in the lab, we need to be able to easily go between the atomic scale and the mass scale that we work with in the lab, right? I know it's been a while since you guys have been in lab, but hopefully you remember putting some things on analytical balances, right? That kind of stuff. So, so in terms of the scale jump that we're talking about, this quantity, a mole, is equal to 6.022 times 10 to the 23rd atoms or molecules, right? So I think the book gives a really good example of the scale of this number. So they say if you took this many quarters and you stack them on top of each other, you could go from the Earth to the sun and back 6 times with the height of those quarters. So this is an insanely huge number. Hopefully you guys can appreciate that, right? It's really, 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 really big. So this number is what gets us from the measurable scale that we have and the atomic or molecular scale. But it's not a special number per se, right? If you guys know, there's this thing called the dozen, right? What does that represent?
12.
12, exactly, right? Why 12? I don't know, right? It's it was convenient at some point, and so they utilized this, but it's 12 of something, right? So in this case, the something that we're looking at converting between is atoms and molecules, right? Could also be ions as well. But this quantity, the mole, is really just a conversion factor. It's something to help us jump from one scale to another. It's not particularly special in that regard. But just so you guys know, the number that the mole is based on, is so 1 mole is equal to 6.022 times 10 to the 23rd. This is the number of atoms of carbon 12 in 12 grams of carbon. 12. Right? So that's where the number comes from. Again, you don't need to know that. That's trivia, right? But it's basically giving us a jumping off point to talk about how to go between the atomic and molecular scale and the scale that we work with in the lab. Okay, so I'm guessing that you guys might be wondering what the heck we're going to do with this. But we can look at, let's say, we're talking about this guy, right? So that is a molecule, right? Everybody's comfortable with that?
Yeah.
Cool. So what if we wanted to know if we have 12, I'm sorry, I'm stuck on the number 12 clearly, 12 grams of glucose, right? We want to know how many, molecules of glucose this is, right? So we want to determine how many molecules of glucose there are in this 12-gram sample, right? So I'm going to flip pages because I need a little bit more room, but I'll write it again up here. So I'm going to kind of go from problem solving, starting with problem solving, and then we'll describe what we're doing as we're going along, right? I think understanding molar conversions without doing them kind of makes it too abstract and hard to understand. So everybody's comfortable with the fact that this type of question is something that you might want to inquire about, right? Does it make sense what we're asking? Yeah, everybody's okay with that? Okay, cool. So, if we want to go from grams to molecules, we have to make a jump to moles first, okay? So, this is what I like to call the Molar-coaster. So if I'm starting off at grams, first thing I want to do is convert to moles, right? That's always my first move. Then once I get to moles, I can get to atoms or molecules. Now we want to know what conversion factors will get us from grams to moles and then from moles to atoms or molecules, right? So we already talked about the factor that gets us from moles to molecules and back again, right? That number is called Avogadro's number. And that's that 6.022 times 10 to the 23rd. We're going to call them formula units, which is just a catch-all term for atoms, molecules, ions, whatevskis, per 1 mole, right? The abbreviation for mole, by the way, guys, is MOL. Super awesome shorthand. We were just too lazy to write that extra E. You want to know the really cool thing? Mm-hmm. We abbreviate molecule. Guess what the abbreviation for molecule is?
No.
It's M-O-L-E, yeah. So that's cool. Not confusing at all, right? But yeah, so when we're talking about moles, we abbreviate that as MOL. When we're talking about molecules, we abbreviate that as MOLE. But yeah, so going from moles to molecules or back again, a conversion factor that we're going to be using is Avogadro's number, right? So now we want to talk about how to go from grams to moles, right? So in order to go from grams to moles, we need our periodic table, which I have. Oops. Okay. So the thing that takes us from grams to moles on the periodic table is the molar mass, right? AKA the atomic weight, right? So where is that on the periodic table? Where is the atomic weight for an element found or for an atom found?
It's underneath on the bottom.
Yeah, exactly. So it's this number in the bottom of the box, right? So if we want to know about the molar mass, aka the atomic weight, right? We just look to the periodic table. Oops, sorry. And I believe in chapter 4 there was a little bit of information about how to find the molar mass for compounds or molecules, right? If you didn't look at that before, that's fine, no problem. We're going to look at it right now. But if we want to find the molar mass, so this is from the periodic table where we get the molar mass of the atoms, right? So that's looking at the molar mass of an individual atom. So if we want the molar mass of a compound, we add the molar masses of all of the atoms in the compound. Or molecule, right? Any questions so far?
No. Okay. I might have a stupid one.
No, not at all.
So, because in this glucose
Yes.
Compound, it says that there's 6 carbons and 12 hydrogens.
Mm-hmm.
So, would you multiply that by the atomic mass? Okay, sorry.
Yes, exactly. And that's what we're going to do. No, that's great. That's really great. So just a reminder that the chemical formula, right, tells us about what atoms are in the compound or molecule and also how many of each one there are, right? So if we know that carbon, and I have my periodic table here, so carbon has a molar mass of 12.011. Now the units of that we haven't talked about up to this point, but the units of molar mass are always grams per mole, okay? Always, 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 forever, for the rest of your life. Molar mass, grams per mole, right? So if we know that carbon has that molar mass, and we know that there are 6 of them, we just multiply it by 6. We know that hydrogen has a molar mass of 1.008 grams per mole, and we know that there are 12 of them, so we multiply by 12. And lastly, we have oxygen, which has a molar mass of 15.998 grams per mole. And we know there's 6 of them. You guys are going to have to be my calculators because I don't have a calculator handy right now.
So carbon is 72.066.
Mm-hmm.
Hydrogen is 12.096. And oxygen, 15. And oxygen is 95.988.
Word. I had it in my brain because I did it yesterday, but I wasn't 100% sure, so I need to back up. So now we take all of these guys, right, which is the molar mass of each one of the atoms multiplied by the number of atom in the molecule, and we add them all together, right? Oh, do you want me to leave that page for a second? Sorry, guys. Give me another sec.
I got 180.15.
Anybody else want to back up Jessica on that?
I got the same. Yeah.
Cool. So we've got, oops. We've got the molar, oh my gosh, you guys. Wow. Molar mass, there it is. Oh boy. Is 180.15.
15.
grams per mole. Perfect, right? Okay, so now this is the factor that's going to allow us to go from grams to moles, right?
Okay.
So this molar mass is what we need to go between those two, right? So now this is going to be similar to what we did in chapter 1, chapter 2, basically a million years ago, right? But we're going to do some dimensional analysis again, right? So we said we want to know how many molecules of glucose are in 12 grams, right? You guys remember the railroad tracks? Are you having flashbacks, panic attacks, PTSD?
Really liked the reference. I've always struggled with conversions, and I thought this was like a super easy way to do it.
I don't know why everyone in the world doesn't do it this way. I'm like, this makes so much more sense to me. Like, I don't understand math people at all, but this works for me. Don't tell them I said that, all the math people. Okay, so the first thing we're trying to do is go from grams to moles, okay? I'm a super visual person, you guys, so I write the Molar-coaster down every single time I do this, right? If you can memorize that Molar-coaster, just write it down at the top. You don't have to think about what you're trying to do, right? You can literally see where you're trying to go. So if I know I'm trying to go from grams to moles, right? What's the first thing that I need to put on the bottom here? Grams, exactly, right? Specifically grams of glucose, right? So I have grams of glucose here, right? So the 180.15 is going to go on the bottom with grams, right? And then this per mole, remember, when we have one of something on the bottom, we don't write the one, but it's implicit, right? So this is 1 mole of glucose. Oops, sorry, 12. Right? You guys still all right with me?
Yeah.
Questions? Cool. So now grams of glucose cancel out.
So you're left with 12 grams over 180.5 grams.
But we're not quite done yet, right? Because there's another step on our molar coaster to get us to molecules, right? So what factor do we need to get us to molecules? Avocado's number, right?
6.022.
Yeah, that one. So, specifically, we have moles of glucose here, right? And avocado's number has molecules of glucose per 1 mole of glucose, right? So before we were writing it in its general form, right? This could be anything, molecule, atom, whatever, right? But now we're talking specifically about glucose, right? So does the 6.22 times 10 to the 23 go on top or bottom here?
Top.
Top, right? Is everybody okay with that?
Yeah, I now officially hate the condensed names, mole versus mol. It's just, can we not do that?
You can write them all the way out. That's totally fine. But my handwriting is so bad. Are you kidding me? I gotta condense somehow. All right. So now moles of glucose cancel with moles of glucose, right?
Mm-hmm.
And now all we have to do is the math, right? So I'm going to simplify that while you guys do the calculations. But we have 12 times 6.022 times 10 to the 23rd divided by 180.15. And this will be molecules of glucose for Jessica, so she doesn't have an aneurysm. Right? So this is again where it's very important to make sure that you know how to use your your scientific notation in your calculator. Right?
Do you recommend, since we have the same one,
Yep.
to go into scientific first before you even do the problem?
Whenever you're dealing with molecules, it's going to automatically do that for you because these numbers are too big for the screen to display. You know what I mean? But yeah. Just so that everybody's with me, does everybody remember how to do scientific notation with a calculator? Usually the EE function or 10 to the X, something like that.
I use the carrot.
Be careful with the carrot, okay? So the reason why I don't use the carrot, I recommend against it, is because especially when you start doing big numbers like this, sometimes when you put the carrot, if you don't put parentheses around this whole thing, it can accidentally do the power of 10 in a weird order, if that makes sense. So that's why I always use the EE function or I think some of the calculators look like that, right?
Oh, yeah. Oh,
Can you
I
show me
see
what
that.
calculator you have?
Yeah, I see. There's a button.
Yeah. Anyone else have questions about how to do cyano in your
Oh,
calculator?
I got a syntax error.
Do we need to put times 10?
Sorry?
Do we need to put times 10? And then parentheses? I mean, times 10 and then on the 6.022 times 10. 23.
So the way that I would put this in my calculator, and again, I have, you guys remember the type of calculator that I'm using? It has the EE function. So the way that I would put this in, I would have parentheses, 12 times 6.022 EE 23 end parentheses divided by 180.15 equals sign.
4.013232. Now, how do you want me to round up? Like sig figs or?
Yeah.
Okay, yeah. So 4.011 times 10 to the 22nd. Is that right?
Yeah, that sounds reasonable.
Back me up, folks. Back me up.
Yeah, that's what I got too.
Oh snap!
Jorge?
Because of syntax.
Okay.
It's okay, Jorge. It's okay.
So what do you think, guys? Pretty straightforward?
Yeah, I think it. Yeah, I think so.
Cool.
It just looks scary.
It's only because
does
we're
look
dealing
scary,
with
but-
crazy big numbers, right? But other than that, like we're really doing simpler problems than we were when we were just doing dimensional analysis, right? Because here we're only really converting between three things, right? Kayla, why I wrote 4.011 as opposed to rounding somewhere else, is that what you mean? It doesn't matter. So we're not doing significant figures, right? So technically it doesn't really matter where I rounded. So yeah, good question.
Just to clarify, when you say EE, I only press the EE button once, right? Not twice?
That's correct. Yes.
Oh.
Yeah, it's one button. So, and again, they're different on different calculators, but the EE function on my calculator is a secondary function. So I have to push the second and then the button that has EE above it. No problem, Kayla.
I don't have an EE, but I have an EX. That's the same thing.
Let me.
Otherwise, I just have like the times 10x or times 10n.
I think you want to use the times 10n. Is there one at the bottom of your calculator where that's a secondary function? I'm trying to remember because I know what that calculator looks like vaguely, but yeah, I think you want the 10 to the.
Okay.
Yeah.
I mean, it worked, so.
Yeah. The main thing is just always err on the side of lots of parentheses, right?
Yeah.
So just to make sure you're not accidentally flubbing things up. Cool. Other questions about that one? Were you able to get that, Jorge?
Yeah, I was just pressing the EE button twice.
Ah, gotcha. Okay, cool. Okay, so let's do another example. And let's go from molecules to grams. Okay, so let's say we have 1.25 times 10 to the 25 molecules of, let's go with methane. And we want to know how many grams. Of methane that is. Right? So, just as a reminder, I always write my Molar-coaster up at the top. Right? And I know the molar mass gets me from grams to moles or moles to grams, And Avogadro's number gets me from moles to molecules, right? My daughter is screaming in the background. I have to like wait a second and like, no, that's just fun screams, right? She's not dying, right? Okay, so now instead of going this way, right, we're going to go the opposite direction, right? We're starting at molecules, jumping to moles, and then jumping to grams, right?
Right.
Thank you, staff. Okay, so we have 1.25 times 10 to the 25th. Molecules, I'm sorry, I can't write that word out every single time, Jessica. I love you, but I'm not doing it.
Okay, I understand.
Especially when it comes to the dimensional analysis, the railroad tracks, things get crowded.
Yeah.
So, what's our first move going to be?
We gotta get to moles.
Correct, right? So we want moles up here now, right?
Mm-hmm.
Yeah?
Yeah.
So for every 1 mole, I have 6.022 times 10 to the 23rd molecules of methane.
And that's for the Avogadro's number? Or?
That's right. That's Avogadro's number, yep.
Is it avocados?
I call it avocados just jokingly. It's Avogadro, yeah. I guess I probably shouldn't do that since this is going to be on the internet forever. So it's my cheap laugh in class, you know. I've got the equivalent of all the dad jokes for teaching chemistry. So what's our next move going to be after this?
Oh, we gotta go from moles to grams.
Mm-hmm. So what do we need to do to get to grams from moles? We need to find the molar mass, right? Yeah. So that's the daddy M, right? So the molar mass for methane is going to be molar mass of carbon plus 4 times the molar mass of hydrogen. 16 something?
I got 4.032.
For this. You just multiplied this, right?
Yeah,
Now you got to add it to the 12. Yeah, no, you're good. I'm already skipping steps. That's how lazy I am. Sorry.
Yeah, 16.043.
Everybody okay with that?
Yeah.
Cool. So I don't really have enough room to write that up here, so I'm just going to extend it down here. It's kind of ugly, I'm sorry. But I have moles of methane on top, right? So I want moles of methane on bottom here. So for every 1 mole of methane, I have 16.043 grams of methane, right? I apologize for the messiness. So I'm going to rewrite it down here just so it's a little cleaner.
Now that I've learned how to write grams per mole, I'm like writing out everything.
Honestly, I'd much rather you get into that habit than a lot of the time. So this is the one that I see a lot is students will just write grams. Oops, I wrote it down and you can't see it. They just write grams for the molar mass. And I'm like, it has the units in the name. Molar mass. Molar mass. You got grams, you got moles. Gotta have them both. Any questions about what we did in this problem? So is this going to be a big number or a small number?
About to find it. Would it be
It's
helpful
small.
to find your molar mass like before you start your dimensional analysis or conversions?
You can, yeah, absolutely. The only thing is you don't always need the molar mass, so you're not always going to be going all the way from one end to another, right? Sometimes you just want to go from here to here, or here to here, right? Or here to here. So depending on the type of problem, if you know you're going to need a molar mass, then yeah, you can calculate it at the beginning. Doesn't particularly matter, but yeah.
Okay.
Yeah.
I got a huge number. Did anyone else get a huge number?
How huge?
Like 3.329 times 10 to the 48th?
No. Mm-mm. So, basically, just looking at this, right, without doing... Sorry, go ahead, Jorge.
I did the same thing. We're around there.
Yeah. So, when you divide powers of 10, right? You guys remember this from a million years ago? If I have 10 to the 25th divided... Yeah, they subtract, right?
Right.
So this is going to cancel to give us basically 10 to the 2 on top, right? So the actual math that we're doing here is really this, right? So I'm a big fan of whenever you're doing these problems, if you get a crazy number, try and think about why, and try and simplify what you're putting in your calculator to see if you can make it a little bit easier for yourself, right?
Okay. Then I got 3.329 times 10 to the second.
That sounds reasonable. Anybody want to back her up on that?
I'm almost there.
What she get?
Cool.
I think I'm a little off. 3.3.
I got 333.008.
Yeah. I think that's just a calculator thing, though, right?
Is it a rounding thing?
3.33?
Yeah, 333.01.
Yeah, so I'm guessing that it's just a digi somewhere, but no big deal.
Victoria got that too?
I got that too.
Yeah, no, that's fine. So this would be an issue of rounding, right? Which again, we're not really going to worry too much about,
Okay.
right? Because these numbers are basically the same, right?
Gotcha.
Does that make sense, guys? So, did you guys have any intuition about the fact that 10 to the 48th grams of something was probably crazy pants?
Mm-hmm.
Cool.
Yeah.
I mean, it's okay if you didn't, but that's the first thing that you want to try and be thinking about with these problems is, does my answer make sense, right? So if you're going from grams to molecules, right, you're starting out with a really small number, and going to a friggin' huge number, right? So if your answer isn't huge, then you did something wrong, right? But if you're starting out at molecules, then you're already starting out with a huge number, and now you're going to make it teeny, teeny, tiny, right? So if you get a really big number, then that means you did something wrong. Does that make sense?
Okay.
Cool. I honestly, and you guys don't have to do this, but I do the powers of 10 math. I get that out of the way before I put things in my calculator. I think it's easier, especially if you're not super comfortable with that. And it's a way that you can double check your math, right? So if you're still kind of struggling with whether or not you know how to put scientific notation in your calculator, it's really a nice thing to be able to do this simplification so that you can check yourself, right? Especially on a test or a quiz or something like that, it just gives you a lot more confidence, right? Question, Steph?
Yeah, so I'm just thinking like the moles, or is that like, you probably already said this. It might be a really random question. I'm just thinking out loud.
No, that's
like,
okay.
Molarity, like in like is it a concentration in a substance? Like will we see it like
Yeah. So the word that you used, molarity, is actually a type of unit that we're going to get into in a few chapters. But molarity is not the same thing as moles, right?
Okay.
Molarity is moles per liter.
Okay.
Okay? And this is a concentration.
Gotcha.
Right?
I actually am thinking of like past labs, and I'm like, oh, well, there's
Yeah, absolutely. Especially like biolabs, I think a lot. This is a really a common unit, right? But it does involve moles, right? So it is very common for us to use this quantity, moles, and not necessarily always grams, right? So there's different motivations for why we might use one over the other, and different types of quantities will use moles, and other ones will use grams. So it's actually much more common for us to work in moles than grams. But we can go back and forth, right? So it doesn't really matter. I mean, it doesn't not matter, right? But we can definitely convert between the two, so. Cool. Questions about this so far, guys? All right, so let's talk about one other instance where things get a little more tricky. Not a lot more tricky, just a little.
Scary.
It's actually not that bad. Right, so we had our Molar-coaster, and we said the molar mass will get us from grams to moles, and the Avogadro's number will get us from moles to molecules. Sorry, this is bad. Sorry, I'm so sorry, you guys. You get me. So we'll get us from moles to molecules or atoms, right? So the one thing that we haven't talked about is if you want to go from moles of one thing to moles of another. And this requires the molar ratio. Okay? So, let's say we want to know how many moles of oxygen are in 12 grams of glucose. Right?
Glucose has 12 hydrogen, doesn't it?
Sorry, thank you. My bad. I just
Good
kept
catch.
kept going on those 12, the sixes.
You were loving the dozens today.
I know.
Or not loving the dozens.
All right. So, if we want to go from grams of glucose to moles of oxygen, right? Our first step is just what we did before, right? Grams to moles, right? I'm using this one particularly because we've already calculated the molar mass, and I think hopefully you guys have an idea of how to do that. So we would start off with our 12 grams, I'm going to write it correctly this time, of glucose. And we had the molar mass of glucose was 180.15 grams of glucose per 1 mole of glucose. Right? And again, I'm not a wizard, right? This is just from our previous calculations. We got this. So now I want to go from moles of glucose, right, to moles of oxygen, right? So what needs to go on the bottom here? You're muted, Steph.
My dogs are barking. Oh, there I go again. We go on the bottom. 1 mole, right?
1 mole of
glucose.
perfect.
I want to say sugar, like every time.
Yeah, that's okay. Samesies. There's just a lot of different kinds of sugars.
Right.
Okay, so what we need to know now to complete the molar ratio, which is this part, right? This is the, molar ratio, right? Is how many moles of oxygen there are per 1 mole of glucose, excuse me. So if you had to guess, what do you think it would be? For every one of these guys, how many oxygens do you have?
6.
6, exactly, right? Oops, sorry. I just really like the number 6 today, you guys. I don't know. Right? So for every 1 mole of glucose, we have 6 moles of oxygen, right? So the molar ratio in this case comes from the chemical formula, right?
Okay.
Does that make sense?
Mm-hmm.
Cool.
So it's gonna come from there?
When we're talking about going from molecules of one thing to when we're talking about going from moles of one thing to moles of something within this compound, that's when the molar ratio is going to come from the chemical formula, okay? Next class, we're going to talk about going using the balanced chemical equation to do these kinds of molar conversions, right? And then we'll be using another tool. It's still a molar ratio, but then it's going to be from the balanced chemical equation. So that's where we're going with this. Does that make sense, Jorge?
Yeah.
Cool.
So how would you read this? Like once you've solved it, would you say how many moles of oxygen? So would you say there are 4 per moles of oxygen or something like how do you read the final answer? I guess we're not there. I'm jumping ahead a little bit.
So the answer is always going to have units of what you're being asked for here, which is moles of oxygen, right? What'd you get?
Getting like a super long number.
I got 0.3996.
That sounds right.
Oh, I did too, but then I just made it 4.
Oh.
996. Yeah, basically samesies, right?
Yeah. Okay, so they're at 0.3996 moles per oxygen and 12 grams of glucose.
Exactly. So there's 0.3996 moles of oxygen in 12 grams of glucose. Exactly. Right? Questions about that, you guys? How we feeling?
We're doing chemistry.
I know.
We're doing math is what we're doing.
But okay, so the thing is we're gonna be moving into doing this with chemical reactions, and then it's kind of like recipes, right? So now we're talking about how do we make this much of something, or how much of something can we make starting with this much of our reactants, right? So that's where we're moving with this. So it really is chemistry. By the by, I posted some videos with chemical reaction types. Did you guys get a chance to take a look at those?
No.
They're demos. Ashley, is that you?
No, it's me, Zainab.
Oh, Zainab. Aren't those cool?
Yeah, it was so cool.
If you get a chance to look at the videos, so they honestly do way cooler stuff than we can do in the lab. Because there's liabilities issues with having students in a lab, but they do really cool, fun examples of all the different chemical reactions. And so if you get a chance to watch, they're only like 3 to 5 minutes each, but they're pretty cool. So I highly recommend looking at those. Hopefully it'll get you a little more jazzed about what we're doing. Any other questions, guys?
I just got overwhelmed thinking about balancing